So it's my pleasure today to welcome Professor Balan to be our One World Minds seminar speaker for this week. He is a professor of applied mathematics at the University of Maryland, has a lot of research expertise going back for not too long. He's still a fairly young guy in harmonic analysis, frame theory, has really influential early work in phase retrieval and phaseless reconstruction that I have enjoyed reading, and has a lot of other service activities besides organizing the FFT talks that he was just discussing before we started the seminar, is also a managing editor for applied and computational harmonic analysis and does 1,000 other things. So it's really my pleasure this week to invite Radu to tell us everything he knows about low-dimensional Lipschitz embeddings and invariant permutations.
Mark, thank you so much. Thank you for this kind introduction, and thank you for the invitation as well. Thank you and the other organizer, Ryan, and everybody else. Thank you all for attending this seminar today. So as Mark was saying, the topic today, the one that I like to talk about, is about embeddings invariant to permutations. And so just to give you a high-level acknowledgement, obviously, we always thanks to the sponsors, NSF and Simons Foundation. And what I'm going to talk about today is a joint work that with Navid Hagani, former student of mine at UMD, and Manish Singh from Verisk Analytics in New Jersey. And recently, that is yesterday, we posted a preprint on the archive. You can find details, proofs, and some other results there. Just to give you an overview, a high-level view of the problem, here is kind of a diagram. So imagine that you have the finite group of permutations or a subgroup of permutations, Sn, that acts on the linear space V. The problem today is to construct bi-Lipschitz embeddings of the quotient space. And that would be the space of orbits, so the quotient by the equivalence relation induced by the action of this group. And the distance on this metric space is the natural distance, that is to say the minimum distance between two representatives of the equivalence classes, x hat and y hat. What we want to have the bi-Lipschitz embedding. That means a map alpha eventually that takes equivalence classes, x hat and y hat, maps into points in Rm in such a way that Euclidean distance in Rm between alpha x and alpha y is comparable, it's equivalent up to constants to the natural distance between the orbits, right? We call the range of alpha performs an embedding or a latent representation of x and y, okay? Now, today we're going to focus on this case when the vector space V is a space of rectangular matrices n by d, or n by d. Okay, and two matrices, x and y, are equivalent if they are row permutation, if they're equal modulo row permutations, meaning that y is p times x for some permutation matrix p in Sn. Okay, Sn is going to denote the group of n by n permutation matrices. Okay, well, here is, again, table of contents, but I'm going to start with the motivation, right? Why am I looking at this problem? Well, in my case, the starting point was a problem in graph deep learning. And here is how to formulate it. Imagine that you are given a data graph, and there are plenty of applications, examples, social networks, transportation networks, and so on. Protein networks, chemical networks. I'm going to actually give you some examples specifically in chemical and protein networks. Now, a data graph is composed of two pieces. One piece of information, it's an adjacency matrix or a weight matrix. Typically, that's a symmetric square matrix. I'm going to call it here capital A. I mean, this is just for this particular example. And the data matrix X. This is a matrix whose number of rows is the same number of nodes in your graph. And the number of columns represent the features, the input features per node. Okay, each row corresponds to a feature vector per node. And the problem I am going to present now, talk about now, is that you'd like to perform an inference own graph, but that is to say, you like to construct a map that takes these two pieces of information, the A and X, the adjacency matrix and the data matrix X, returns a label or some characteristic, but that characteristic is of the graph. It's not per node, it's per graph. For instance, you may want to classify the graph, and that means to return a label in a finite set of possible classes, or you can perform regression or prediction on the graph, in which case you could return a value on, real valued, complex valued, whatever range, domain range for this function f you'd like. But the point is, the task that you need to perform is characterizes the entire graph. Okay, is not per node, it's per graph. If that is the case, then naturally the function that you need to construct, that you want to construct, should be permutation invariant. In what way? Well, that function should be invariant if you relabel the nodes. In other words, if you permute the vertices. And here is what explicitly this means. So if you take a permutation matrix P in Sn, you conjugate the adjacency matrix by PAP transpose. That's what the new adjacency matrix after vertex relabeling. And the new data matrix, which PX, you row permute according to this relabeling. The function, the value of the function f should not change. So f should be invariant to this type of conjugation. Okay, that's the motivation. Now, if this is what you want to do, the natural question is, how do you do it, right? How do you construct such invariant functions, such functions invariant to permutations, right? Now, today I'm not gonna give you the I guess a full theory of functions that take two such arguments, right? And how to construct f. I'm gonna actually focus on a specific architecture that implements such an invariant function. And I'm gonna focus on a particular component of this architecture. Specifically, the architecture I have in mind, let me actually skip one slide and I kind of come back, is composed of three components. One is this GCN or GNN, that's a graph convolution network or graph neural network, I'm gonna tell you in a moment, that takes this input, X and A, the adjacency matrix and the data matrix A, and it turns a latent embedding or representation of this input, this matrix Y. Then there is this component alpha that we're going to focus on, and finally there is a fully connected neural network that performed that learning task I mentioned earlier. Now, what is a GCN and what does it do? Well, so there is quite a broad set, literature on the topic. I'm not going to discuss too much about it, except to say, I mean, here, if you want details as to how the input gets mapped to output, the only thing I like to say is that a GNN or GCN is not invariant, but rather is covariant or equivariant. People say in, I guess, neural network literature, it's equivariant in the sense that if you relabel the nodes, that is to say, if you conjugate the matrix A by PAP transpose and the data matrix A, so it's PX, right, exactly the way we assumed earlier, the output is not invariant, but it's covariant changes. So you also get a raw permutation of the output Y, provided that, well, in this particular case, the biases B1 to BL also are changed by the same raw permutation, right, P. For instance, if B, the biases have constant entries or the rows were identical, then of course that's not an issue, right? So the point here being the GCN or GNN, if you want to keep in mind, this is not invariant, it's equivariant. It represents your input data into a latent representation, this matrix Y, but the Y changes, the rows of Y changes just the same as you change the nodes on the original graph. Okay, so the GCN doesn't necessarily solve the original problem. It's a good component. It's a it's an important component. We're going to use it, but it's not invariant. It's covariant. Given the fact that the GCN embeds your input data into just the matrix, right? The same number of rows as the number of nodes, and perhaps a new data here, then the problem now becomes, if I like to be permutation invariant, this is actually what the second component over here does. I'd like to represent this matrix Y into some other form, the Z, which is invariant to raw permutation of Y, but in such a way that is also faithful to Y. In other words, I like to be to be injective modulo row permutations, right? That would be the task of this alpha, is embedding. And once you have this embedded version Z, which is invariant to row permutations, of course, you can, next use your favorite neural network, fully connected or otherwise support vector machine, which is just one layer, for instance, to perform the learning task, classification or regression, if that's what the final object is. Okay, so as I mentioned, today I'd like to talk about this component alpha over here, okay, which is the permutation invariant representation. I see some questions on the chat. I have it here. So there's a question saying whether the sigma should be invariant for this task as well. Yeah, sigma acts entry-wise, so it is kind of sigma acts entry-wise on is the same function sigma on all the entries. So implicitly, it is invariant to the relabeling. Yeah, so the second question was about whether the interest is graph labeling or node labeling. So it's graph labeling, right? That is to say, it's a label per graph, not per node. It's not per node, just entire graph. Okay. So, all right. Just to fix the problem and to fix the notations, our space V is a space of n by d matrices. Okay, and the action is induced by the permutation, by the group of permutation matrices Sn, which act on V by left multiplication, meaning that two such matrices, x and x prime, are equivalent if and only if there exists a permutation matrix P such that x prime is P times x. Okay, R and D with a head is going to denote the quotient space, the space of orbits, and we're going to use the natural distance on the quotient space induced by the Frobenius norm, meaning that this is a minimum of Frobenius norm difference between, let's say, x1 minus px2, where you let P run over the group of permutation matrices. Yeah, you could change the Frobenius norm into any other norm you like. I mean, eventually, all norms are equivalent of finite dimension spaces, and here you're going to get distances which are equivalent, Lipschitz equivalent modulo constants. But, let's focus on the Frobenius. Now, the distance, so this natural distance, luckily on the space Rn by d can be computed rather easily. And this is what this part over here on the slide says. In order to compute the natural distance, if you square both sides, I mean, if you square this norm, you end up with a norm of x1 square, norm of x2 square, because that's the Frobenius norm is invariant to action of orthogonal group, and minus 2 the Hilbert-Schmidt scalar product between x1 and px2, right? And minimizing means you want to maximize this cross product, which means you want to maximize the trace of px2 x1 transpose. Well, while this looks like a combinatorial optimization problem, a discrete optimization, actually it's an exact, it's easy to solve. The reason is that this is known as a linear assignment problem. Its convex relaxation is exact. So the objective function is linear in the matrix P. I'm going to call it W here. Okay. But the convex hull of the constraint, the set of permutation matrices, well, this is a set of doubly stochastic matrices. The right-hand side, so this is now a convex optimization problem, and the optimum solution, the maximum, coincides, is equal to the maximum of the original problem, right? And a maximizer here is a maximizer on the right-hand side as well. If that is unique, then both would have exactly the same optimum solution, the same optimizer. Okay, the right-hand side is it's a linear program, right? Maximizing the trace subject to these linear constraints and can be solved efficiently in various ways. Anyhow, this is just as a side remark, just saying that the natural distance is relatively easily computable. The question, though, remains, and it's basically put here on this slide. What we want to do is to construct such a map alpha, right, that takes a matrix and by d returns a finite vector Rm in such a way, so, and they have two constants a and b as well, in such a way that if two matrices are row permutation equivalent, right, they are equivalent, equal to one another via row permutation, then alpha should map them in the same place. And vice versa, if x and x prime are mapped by alpha in the same have the same representation in Rm, then the two matrices should be row equivalent, And finally, the third condition here is this bi-Lipschitz. So we'd like, actually, yeah, it's a typo here. It's not a Lipschitz. We want really a bi-Lipschitz ultimately. That means we like to, for some two constants a and b and any index x and prime, we like the L2 norm of the difference in latent of their latent representations, alpha x and alpha x prime. That L2 norm to be bounded above and below up to these constants by the natural distance between x and x prime, okay, between the equivalence classes. That's the problem, and that's what I like to do for the next remaining time, I should say. Okay, there is one solution at some level. It's easy to come up with, and that is, I call it universal embedding, is to say, look, take such a matrix or equivalence class and replace it by a measure. Right, it's a probability measure. You just put Dirac's in acting on RD. This is a row space, okay, or space of rows, and you put delta there. You translate to these rows and take the average of deltas to get a probability measure. Well, this is good in the sense that, for instance, the Wasserstein to distance, if you do a little bit of computations, ends up to be equivalent to the natural metric. In fact, in this case, might be exactly equal. And the Wasserstein 1 distance, it's also known as the Earth moving distance, eventually leaves to a norm on the space of signed Borel measures. So that's great. You have a lot of machinery behind it, right? The whole optimal transport theory. The only problem here is that the set of probability measures, while it is a convex set, it's infinite dimensional. So this is not exactly what we want, because we want a finite dimensional representation of our quotient space, right? So I mean, it's good theoretically, but not so good practically. Now, what people do in such cases, if you end up with objects in infinite dimensional spaces, you project them on finite dimensional sets. And the idea is to project this measure on a finite dimensional space. How you do that, for instance, one method is to use kernel method. You can use a family of functions and take the measure, and you integrate those functions back to measures, and you end up with this sort of averages here, right? You take your function, you evaluate on those rows, and you average them. Right. Now, this is not only a popular method, but I mean has been used and is used in practice. And I'm gonna just provide you a few pointers to what type of results people obtained. And I'm gonna tell you there is a shortcoming as well in just a minute. But this is not eventually what we're gonna be interested in. Now, possible choices I mentioned here. So it's a huge literature on polynomial embeddings or algebraic embeddings. Essentially, you would like to construct the ring of invariant polynomials in that case. And I put a number of references here. I mean, by no means it's not exhaustive. The first ones are maybe more recent, in the past 10 years or less, that are coming in the context of deep learning, graph deep learning, for instance. But then you go back, to construction of invariant polynomials. Mentioned here Kemper books, and well, you can go all the way back if you want to Hilbert, maybe even more, right, in between the huge literature, more than a century, how to construct invariant polynomials. Now, another family is the Gaussian kernels. That's a very natural choice. You take your X rows and you fix a set of centers and just compute these Gaussians, right? In that case, your representation will be a sum of Gaussians sampled at the rows with various centers. And again, number of literature here. Fourier kernels, it's another popular method. These are complex exponentials. It's a complex embedding. You take the complex exponential, your x is here, taking a product with a fixed set of vectors, omega j frequencies, if you like to call them. If omega j come from a lattice, integers, for instance, this you can connect, in this case, the Fourier embedding with the Prony method, right? And there are a number of very good and interesting results. I mentioned, for instance, Wei-Lin Li, who obtained recently bi-Lipschitz estimates for such functions. It's super resolution problem. Now, what makes it slightly different than the general super resolution problem, and I know a number of people actually work on these complex exponentials in many ways. So it's the fact that here you have a finite linear combination of exponentials with coefficient 1. So it's not an issue of recovering the coefficient in front, but just the exponents. Anyway, so there are many methods. I'm not claiming any exhaustive list here, but if you look carefully, as far as I know, I do not know of any bi-Lipschitz, let's say global bi-Lipschitz result about these embeddings. Okay, there is an interesting result in the polynomial case and by James and Cahill collaborators that in fact they show that you can make it Lipschitz but not bi-Lipschitz. It has a problem when you approach 0. It's also okay on compacts, on some compacts, but at least on compacts. But our goal is to do it on the entire space. Okay, that's what we want. Okay, so having said that, excuse me. Let me tell you actually a different method, right? That's a different approach that I like to use. And this approach is based on the following observation, that if you look at the sorting map, down arrow, that takes a vector and dimensional vector, and it turns sorted vector. You, for instance, sort monotone decreasingly. Well, excuse me for a second. The sorting map ends up to be an isometry on Rn, on the quotient space. So because of that, obviously, it's bi-Lipschitz, but it's the best bi-Lipschitz you can hope, right? It's an isometry, preserves upper and lower bounds are 1. Excuse me. And now, the result is easy to prove eventually. If you square both sides, you simplify, and then you look at the cross terms. The proof is based ultimately on this rearrangement inequality. You can find it on Wikipedia, or it goes back to Hardy Little Polya book on inequalities. Excuse me for a second. Okay, so our main goal today is to extend this construction. Okay, this works on n-dimensional vectors, but now the question is, how do you do it on matrices? So your entries are no longer scalars for which you can order according to their value, but are vectors. Can we do a similar or some sort of sorting, ordering on vectors instead of scalars, right? And that's what I try to convince you that it is possible. All right, so here is actually how the encoder works. The encoder actually is going to be composed of 2 pieces. The first piece is described here, and this is how it works. So again, recall the equivalence relation to matrices, equivalent modulo row permutation, the natural distance between matrices, right? The minimum distance between representatives in their equivalent classes. Now, what I like to do is to construct the following map. You take your n by d matrix, n by little d, you multiply on right by a fixed matrix A that I'm going to call a key, right, like encoding key, and then you sort the column of this matrix x times A. You sort monotone decreasingly independently the columns. Okay, so you apply the down arrow operator on each column independently. Now, what the key does, so think of the capital D as being an integer bigger than little d. Okay, so in that case, what the key does, it introduces redundancy, right? You take your original matrix x, you multiply by A. X times A is now it's a matrix as well, but there is a lot of redundancy. There is a redundancy in XA compared to the original X. And when you when you sort monotone decreasingly each column, even though you may lose information as to how one column is related to another column, you hope that the redundancies that you introduced here would be able to disentangle and to recover this loss of information. Okay, so the matrix A here, we call it key for this encoder, and the key is called universal, so it's a universal key if in fact this map beta A is injective on the quotient space. I mean, it's immediate to see that this beta sub A is actually invariant to multiplication by permutations on left, that is to say row permutations, simply because here you permute the rows of x times a, right, by the same permutation matrix, and then when you sort monotone decreasingly, that obviously it's invariant to that multiplication by permutations on the left. So it naturally lifts on the quotient space. Now the question is when and if and when this map is injective, right? It remains injective, is injective on the quotient space. And if and when this happens, we call the key universal. Our task is precisely to construct universal keys. All righty. So let's see. So here is the intuition behind, what this key does, and if you have a universal key, what you hope to accomplish. So let me, for graphical purposes, let me illustrate with this small dimensional case. Let's say your matrix has 2 rows and 3 columns. Okay, little n is 2 and little d is 3. For start, let me consider the 2-dimensional simplex, right? The triangle in R3. And these are this is a triangle formed by vertices that have coordinates 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, now take this triangle, take this 2-dimensional simplex, put it on a plane, all right? And on top of each one of each vertex, draw a line, draw an axis, and it represents the columns of the matrix X. So at 1, 0, 0, the column would be, the first column would have these entries, x1, 1, and x2, 2, 1, and that would be these red and green points, right? The second column, x1 to x2, 2, goes on top of the second vertex, 0, 1, 0. And these are the points, for instance, x1 to here and x2 to here, right? The red, so I'm gonna color with red and green the row and each of the 2 rows of the matrix X. So here are the x1, 2, and x2, 2. And finally, on the third column, the third column of the matrix X goes on top of the vertex 0, 0, 1. And these are, here you have x1, 3, and x2, 3. Okay. So imagine you have such a setup here. Okay, now what's next? Well, if you sort each column independently, and you call this matrix Y, then the y11 and y21 would be these 2 numbers over here. Okay, they coincide with x11 and x21 in this case. But in the second and third column, if you look y21 and y22, well, y21 is x22 and y22 is x12 because of the way they are related to one another. You basically switch the order, right? And the same thing happens on the third column. Some information is lost, and specifically what information? Well, remember that our task would be to recover the original matrix X up to row permutations, which means we have the freedom whether to recover x11, x21 in this order or the reversed order. So let's say that we want to recover x11, x21 in this order. But once you sort the second and third column, you basically you flip the relationship between these 2 coordinates, and you'll not be able to recover that just from these numbers over here, right? Now instead, if you look at the planes, the 2-dimensional planes generated by respectively the rows of the matrix X, that is to say the red dots here and the green dots there, if I multiply X by an additional vector of 3 components, okay, if I take X and I put additionally X times a little a vector that may have coordinates A1, A2, A3, and let's say in the case they sum up to 1, I'm representing in this the hyperplane generated by the 2 simplex at the point here. Well, basically what I'm doing, I'm drawing a line, right, vertical to the horizontal plane. I see where it intersects the red and green planes, and I take those 2 numbers and I order them, right? And they become now a new column in my matrix Y in the representation of the data matrix X. Okay. The hope is that if you sample this 2-dimensional space, the plane generated by the 2-dimensional simplex, in sufficiently many points, eventually you'll be able to recover exactly the planes, the two planes, red and green. If you have those planes, then you can recover exactly the relationship between the original 6 numbers, right? You know that you would figure out that the red point over here on the first vertical axis should be connected to, for instance, y22 and y32 here. They belong to the same plane rather than other permutations, right? Other combination of points. That's kind of the idea and the hope that if you introduce redundancy before you sort the vectors, that redundancy would be enough so that after you sort the columns, you recover the data matrix X up to a global row permutations and not just, you know, relative permutation between columns. Okay, so with this, I guess, explanation in mind, I'd like to present you a few results. But maybe before doing that, just want to check if there are some questions about this particular construction, how the encoder looks like, or if there are anything. Nope. Looks all good. Okay. So what I'd like to do now is to show you. Yes. So question about the X times A. So XA is basically the matrix X multiplied with a column vector, little a. So A just stands for a vector of 3 coordinates, 3 components, A1, A2, A3, and XA it's a new column. It's like a 4th column that you had here, right? And you sort, and that's what it is. Right. So I'm gonna discuss 3 results, right? One is the fact that yes, there exist universal keys, and I'm gonna tell you how I can construct them. The other 2, it's about bi-Lipschitz property, and the third one is actually dimension reduction result. Okay, so let me start with the first one, existence of universal keys. It's a big slide here, but what it says is the following. You start with the original metric space, right? The n by d matrices, and natural distance di, realize that it's the same letters. Sorry about that. Hopefully it will become apparent which one is which. You set this capital D. This would be the new number of columns of the embedded, and it's this 1 plus d minus 1 and factorial. So this you know, the sign here is indeed is a factorial, not unfortunately, right? So the capital D is a huge number. It's 1 plus d minus 1 times n factorial. Now the good news is that take any matrix A d by capital D whose columns form a full spark frame. Okay, so full sparse frame means any collection of little d columns is linearly independent, right? And there are plenty of that. And you know, Jameson, Cahill, Dustin Mixon, and you know some other people, Fonso Bandera, they have a very nice paper about the full sparse frames, and you know some other people as well. So I'm not you know, perhaps doing justice just to mention them, but there are plenty of constructions about the full sparse frames. Okay, so take construct such a d by cap d matrix such that the columns form a full sparse frame, and this is good news because such a matrix actually turns out to be a universal key. Specifically, if you take your data matrix X, multiply on the right by this A, right, and then you sort columns monotonically decreasing, you sort them in some order, then this matrix, this map, sorry, beta A hat is injective on the quotient space, which is great. But more than that, it's not only injective, it's also bi-Lipschitz. And there are estimates of the Lipschitz constants. The upper Lipschitz constants is the largest singular value of the matrix A, whereas a lower Lipschitz constant, A naught, what you do, you look over all collection of columns of size, you look over all little d columns of the matrix A, and you look at the smallest singular value, right, of those. And you minimize over all possible combinations. And that would be an estimate of the lower Lipschitz constant. Again, these are estimates. And basically, this is what it means, that the Euclidean norm between beta x and beta y, you can upper bound and lower bound by the natural distance between the equivalence classes x hat and y hat modulo these constants, A naught and B naught. Okay, so that's great. That's the first result, saying yes, you can actually do that. That infinite dimensional representation with a measure, right, a probability measure that I mentioned earlier. Well, you can instead replace it by another object, which is this beta A of x, which is finite dimensional, and you preserve all the metric properties, modulo constants, of course. So it's a bi-Lipschitz representation of that, which is great. Well, we still have this cap d, growing with n factorial, but we'll address in a minute. Now, the second result says, look, actually, this construction, if you can construct a universal key differently with different size, I mean, that is a sufficient condition, right? If somehow you construct a universal key with capital D columns, well, that's good enough in the sense that the induced map is bi-Lipschitz. It guaranteed to be bi-Lipschitz, okay? So the second theorem says that the algebraic property of this one being injective implies a metric property, namely it is bi-Lipschitz. And that's good, right? I mean, at least we have some confidence that if you solve the algebraic problem, you get some stability as far as a representation and possibly reconstruction is concerned. Just like in the phase retrieval problem, if you have if your representation is injective modulo a global phase vector, then in fact you get bi-Lipschitz properties for that. And the third theorem, third result, is to say that, look, even though the original construction that beta A maps you into a huge dimensional space, that capital D that grows with n factorial, actually you can in fact ultimately find a projection. You can construct ultimately a projection from that big dimensional space D to a much smaller dimensional space, and effectively the statement says that for a generic linear operator from this n by cap D down to Rm, well, little m, you just need to choose an integer greater than or equal to 20. You can choose 20 if you want. In fact, I started with little m greater, but the statement is exactly 20, so I should have said m equal to 20. If you compose these two maps, the linear map B with beta A with the encoder I mentioned earlier, this actually is not only injective but also bi-Lipschitz, right? So in other words, you can find bi-Lipschitz embeddings of the quotient space into R2 and D. So the price to pay, it's you just have to increase the dimension by a factor of 2, redundancy 2, and you get the bi-Lipschitz embeddings, right? That's a good news. Now, if you open the box, the bad news is that in order to construct, I mean, the second good news is that this is constructible. It's not only it says that there exists, but in fact it's constructible. However, the bad news is that the intermediary step going from the quotient space to R2 and D, you have to go through this capital D space, right? The little n by capital D space. And that, at least at this point, existentially speaking, grows with n factorial, which is a huge pain, right? But at least they said that in theory there exists a small dimensional representation of the quotient space into this Euclidean space. And
can I ask a quick question?
Sure. Yep.
For the previous result, is there any kind of bound for A0 for the lower Lipschitz bound?
Yes.
Just know it's positive.
Oh, you're asking if I have an estimate of the constant?
Yeah, and I'm wondering what it might look like if you know.
Good question. Good question. No, so the short answer is I don't have. Let's say, even an estimate as this one. But you're right. The proof actually is existential. It only says that the A naught must be positive. In other words, we derive a contradiction that if A0 is 0, you get a contradiction. And in fact, I'm going to comment a little bit on the proof. I mean, that would be but it's a very good question. Thanks. Okay, so the third result was to say that ultimately you can Euclidean embed your quotient space into a space that has dimension twice as big as, I guess, the natural dimension, the dimension of the V space, right? The original V space that generated the metric space. Okay. Now, I made here this comment saying that the embedding you get is, I mean, the result is compatible with the Whitney embedding theorem, right? That was saying you can embed in dimension, roughly speaking, twice dimension of the original manifold. The important caveat is that Whitney applies to smooth manifolds, whereas this quotient space is far from being a smooth manifold. It's not a manifold. So that's what it is. Okay. Good. So I'm actually relatively, I guess, short on time. So I have two options at this point. One is to discuss a little bit, give you some ideas about the proofs, just comment high-level elements of the proof. Or the second option is to show you some numerical results, right? I think that, well, I have, I think, slides for each of the three results, high-level proofs. I would rather just highlight the second result about the fact that any universal key generates a bi-Lipschitz map, because yeah, it has something unexpected somewhere. And then I'm going to show you some numerical results instead. But if you have questions, I'll be happy to return to these slides. So the second result saying that if you have this universal key is going to be always bi-Lipschitz. And I mentioned here the proof resembles a treatment of phase retrieval problem. And Mark, thank you for the question, because that's very much related to the way, I guess, we proved it in the phase retrieval as well. So step number one, so there are like 4 steps, right? The step now, I mean, all in all, the proof is based, it's by contradiction. And assuming that the lower Lipschitz constant is 0, the step number 1 use homogeneity and compactness of the problem to reduce to a local analysis. So in other words, if the lower bound is 0, then it has to fail locally, has to find something locally. Locally, then you linearize. So you can, do a little bit of analysis there, and you linearize your map beta sub A. But what you end up with, ultimately, it's a maybe unexpected optimization problem that is a quadratically constrained ratio of quadratics. Sorry, that's the typo here. So QCRQ, quadratic constrained ratio of quadratics. And step number 3, and this took me quite a lot of time actually, and back and forth, thinking whether that's true or not ultimately, is that QCRQ, which is an infimum of a ratio of 2 quadratics, as the name says, is actually a minimum, is achieved, right? That's step number 3. And there is actually a lot of literature. I mean, I should say that there is some literature on the QCRQ that may convince you that it's not quite a trivial problem. Mentioned here, the bullet, all there are these 2 papers we refer to, and some other people in literature look at this QCRQ. And anyway, the very special type of problems that we have here was not exactly amenable to get the general results from literature. So we had to come up with, tailor, I guess, the argument to the problem. And eventually we showed that the infimum is actually a minimum, right? Once you've done that, then you derive a contradiction to injectivity. But this was a, I don't know, very painful, I guess, step in some sense. So that's a highlight, I guess, of this proof. As I have another slide about dimension reduction. This is a trick that I learned from Jameson Cahill's paper, and also Dufresne has very nice statements about that. But I'll skip this one. Okay, and there is something about the universal keys I can maybe put here, saying this is a joint work, in fact, with Daniel Levy from University of Maryland. We've been looking at what is the smallest dimension cap D that define universal keys. Okay, and it turns out that the smallest dimension D is, well, much smaller than the n factorial, and we have estimates, in some cases to see what it means, what that is. So there is hope, in fact, that universal keys will not necessarily grow with n factorial, or at least d minus 1 n factorial. But let me show you some numerical example, right? What difference would that make? And actually, there are 2 data sets. One is a protein data set, a classification, and there's a QM9, a chemical compound. Let me switch to the QM9 data set, right? Just to comment for a few minutes. So this is a data set about, over 100,000 isomers of organic molecules made up of these 5 atoms. Each molecule contains somewhere between 10 and 29 atoms. There is a description somewhere you can find. So for each isomer, this is the information you are given. So it's a file. The file contains a number of about 19 features that are computed for that particular molecule. We chose one of them, and this is this electron energy gap delta epsilon. And we want to predict, we want to perform a regression or prediction of this electron energy gap based on the information that we have about that molecule. And the information, the graph-like information, is to say, okay, so you construct a graph where nodes correspond to atoms. For each atom, you know the geometric coordinates x, y, z. Well, specifically of the orbital, right? They solve the Hartree-Fock system of equations, right? And from the orbital, they derive the coordinates of each node of each atom, and also partial charge per atom, so-called the Mulliken charge, right? So this is kind of the information you have per node. And of course, the type of atom you have out of this class of 5, and some other physical information per node. This is the input feature matrix, right, per node. And okay, and then okay, we construct, you know, a GCN, a graph convolution network with a number of layers and so on. And we worked with several alpha components, right? That permutation invariant embeddings, right? We tested with 7 components, to be more specific, 7 methods. The first 2 are not permutation invariant. Identity obviously is not, but this is always good to have a reference to understand how you compare with that one. Data augmentation, again, is the identity, but you augment your training data set with additional permutations, right? The ordering, this is based on what I said earlier, except that my encoding key is identity followed by a colon of 1. So you just introduced one additional colon. It's not universal, but you know, we actually show in the paper that such a key, while it's not universal, you achieve injectivity almost everywhere in, you know, some similar concept as in the phase retrieval. So this is ordering a kernel with a Gaussian kernel, sampling, which is you just sum the rows of your latent representation, obviously would be permutation invariant. Sort pooling, the method works by sorting according to the last column in your data matrix X, and there is a set to set introduced in literature, Vinyals and so on a few years back. Okay, and numerically there is also a comparison to a state-of-the-art results that I'm going to tell you in a second in a table who did. Anyhow, so this is how the training is based on the mean square error, right, between output of the network and the delta epsilon, this electron gap energy that we want to predict. You have, you know, behavior of this of the mean square error. What you vary is a little d is the size of these latent representations, right? The outputs of the GCN before you do the permutation invariant component. So you do some training here. There is a holdout data for which, you know, on which we tested once you train on the first one to see how it happens on the holdout. What I like to point out is in case okay, so maybe, I mean, it's kind of a dense here, but the yellow curve corresponds to identity, right? That means you don't do anything special about the permutation. And you see, if you check on the training, for instance, with D100, identity goes all the way down. It's the best. It achieves the best performance, the best mean square error. If you do on the holdout, okay, even at 100, little D100, you lose some, but you know, it's not that bad, right? But now I'm gonna take the holdout data and I'm gonna permute the node. And that identity that is, you know, going down here now goes way up. I mean, all these curves, the yellow curves that you see here, now would be on the same holdout data that you saw before, except that I'm permuting the nodes right in that input graph. Except for the identity and data augmentation, all the other methods are guaranteed to be invariant to permutation because by construction they are that. But you see, with the identity, you lose a lot in terms of performance, right? And here are just some numbers that you get for the mean absolute error with the ordering. So these are kind of the numbers on the training and the holdout. I mean, as I said, on ordering with identity, you get a smaller error, 0.139. That's in electron volt, the unit. But it performs terribly once you go on the holdout and you permute the nodes. Whereas the ordering, performed reasonably well on all of that. To have a reference for comparison, the chemical accuracy, what they say about this one is 0.043. That's I think about maybe 2-3 times somewhere the error we get compared to the chemical accuracy. The best method, Gilmer et al. Achieved a MAE of 0.053, so it's twice more smaller than what we get. But in literature, there are other methods like Coulomb method that achieved the MAE significantly larger than what we get here, even though they kind of optimized for this type of interaction. Again, I did not. Our intent was not necessarily to build a prediction or regression system that outperforms existing method literature, but more or less to understand the trade-offs between whether you cope with permutation invariant with I guess permutation with the action of the permutation group or not, right? Whether you just don't pay attention to it or not. So since my time is out, I'll rather stop here. I have bibliography listed here. As I said, details you can find them in the archive preprint. So I'll stop here. Thank you. And if you have questions, I'd be happy to answer.